let's make a start, guys. So today we're gonna learn all about Hamiltonian graphs, and of course it's gonna go to the wrong screen.
So I thought you would appreciate me being on time rather than me having my stuff. So that's what happened.
Brody, I'm gonna tell you something. You thought wrong.
Really? Would you rather me be late and have my stuff?
Yes.
Good guy. I thought you were gonna be like, nah, every minute counts.
Well, how are you gonna do your work today?
You learn stuff.
Oh my goodness.
To my friend,
So I'm trying to get this. For some reason, this laptop has decided it hates projecting to the same screen. And that's like, what? How did that crash? Hello.
Sorry for the lateness. The tardiness will not happen again.
I'll hold you to that.
Next lesson will be early.
Okay, so guys, today we're going to learn all about
Hamiltonian.
Thanks, guys. We're going to learn about Hamiltonian graphs. So that's our goal today. By the end of today, you will be able to say, I know what a Hamiltonian graph is. So your learning goal for today, you learn about the criteria for graphs to be Eulerian or Hamiltonian. So remember we did Eulerian last lesson. And you'll be able to determine Eulerian, semi-Eulerian, Hamiltonian, and semi-Hamiltonian paths and trails using trial and error methods to solve practical problems. Determine Eulerian, semi-Eulerian, Hamiltonian, semi-Hamiltonian paths and trails using trial and error methods to solve practical problems. There you go. Okay, so let's review. So Eulerian. What's the trick to know if something's going to be Eulerian or not?
It has all even or two odd.
Yeah. Yes. So which one is a pure, or is it, if you just said something's Eulerian, is it all even or can it have two odd?
All even.
All even. If it's too odd, what do we call that? Semi-Eulerian. And that's all that stuff. Says. So, yeah, so if a graph has an Eulerian trail, we say that graph is Eulerian. And so that's just what we did on Monday. So, guys, to start with, can you just like draw those graphs in and tell me if they're Eulerian, semi-Eulerian, or neither?
No, I'm not going to be stupid.
I want you to draw them in. And that also gives me time to do the roll.
Cuts. I got cuts on my hands. Oh, power through. Pretty safe. 1, 2, 3. No ironing, no marble. This is my business. What's the date today? The 18th? Yeah, 18th. Is it a good day? Oh, you're kidding me.
Oops, sorry guys. Alright guys, let's go through the answers. First one, did we say Eulerian, semi-Eulerian, or neither? And what's our reasoning? There's two odd vertices. So that has degree 3, that has degree 3, that has degree 2, that has degree 2. So remember, with a semi-Eulerian, what does that mean? Like sorry, let me take a step back. If Eulerian sort of mean, it has a practical application. Like, we're not just classifying this for nothing. What does an Eulerian graph mean? Yeah, so if this was Eulerian, I could start at any vertex, visit every vertex, use every edge once, and get back to where I started. That's Eulerian. We said this is only semi-Eulerian. With semi-Eulerian, can you start at any vertex? Yeah, so you'd have to start at either the top 3 or the bottom 3, and you'd no. So you still don't repeat any edges, but you'd end up at the other odd degree. You wouldn't end up back at the start, like an Eulerian, which is the case for this one. I hope you found. This is Eulerian, because we have 2, 4, 2, 2, 2. So you could start at any point, use every edge once, and get back to where you started. Because this graph is essentially 2 cycles. So if you started there, you could go along there, along there, along there, back to there, back to there, back to there. Or you could start somewhere else, would be a very similar path. And this last one, what did we say? Neither. Because there's too many odd vertices. No good. Not what we want. Okay. So guys, we're going to have a practice at this. So if you can't quite see up here, that same picture is on page 417 of your textbook. So it shows St Andrews, Kingslake, Yarra Glen, Talangi, Healesville on the map and how they're connected by roads. So I want you to draw a graph with a vertice representing each of the towns and edges representing the direct connections between them. Ignore any towns not listed in the question, and explain why it's semi-Eulerian, not Eulerian. And then write down an open trail that begins at Tulangi and follows every edge only once. And explain how you could tell this trail would end at Kingslake. So I'm going to give you 4 minutes to do that.
She ran at me and I just picked her up.
It's funny, I was actually picturing, like, you know, the song, the end song.
Like,
yeah, like, that was literally what I was.
From?
Dirty Dancing. I honestly hadn't thought why. I just mentioned something about pop culture related to like
I've
things
never
you
seen that
guys.
movie.
Where are you going? St Andrews. The St Andrews.
That is Oh yeah, it's above saying Must miss
So it's like there. And then it's connected to Kings Lake.
Kings. Kings Road, am I right?
Kings
Yeah,
Lake
what?
is connected to.
I heard Kings Road. I can't play it like this. Maybe I did it with all of last week. Plus, I didn't feel like it. But since you had to be back up now, because I couldn't even watch Netflix. So then I feel like yeah, mine's red bars right now. I swear they didn't make it keep track.
St Andrews Kings Lake.
Is it that? I don't know, just oh. What's this one? The latest one's trash. What's that? I haven't played it.
There we go, boys. Have I missed any connections there?
I don't have it either. The Viking one?
I think I have missed the
I'm talking
connection.
about the Viking one. I'm talking about the old one.
Tulangi goes to
Oh,
Kings
I
Lake.
forgot about
Oh, Tulangi would have a matchup with Yarra Glen.
I forgot there was a Viking one coming. Vikings were both too long ago. Oh god.
I suppose St Andrews must Wait, that can't be right. Oh no, that's right.
So is there a connection between things like
I'm assuming Kings Lake and Yarra, yeah, because we're ignoring that town of Casella or whatever that is. So technically, you go Kings Lake Casella there because we're ignoring Casella. It's saying you can go direct there.
that maybe you can go from Yarra to
Yeah, so Yarra and Tulangi and Yarra and Healesville, and I've also said Yarra to St Andrews because it looks like I'm just doing my best judgment here, but it looks like St Andrews, these two main roads meet up like theirs. Not super, but
Good enough.
that's the only way that it becomes semi-Eulerian, which the question implies that it should be. So, well, actually, if you turn the page, because it's an example, it should show you what it looks like. Yeah, righto. Okay. I'll give you another couple minutes. Never mind. I'll hold new horses. Shanti, if you get your keys, can you come back to school and buy us all Maccas?
I thought you were going to say come back to school for the rest of the day, but I was going to say she should.
Just like a sneaky frozen Coke would be nice. Is that like just... That's the second time today I've heard someone say a frozo. I've never heard that before in my life. Is that like a Bowen thing?
Isn't it voted? What, voted? Yeah, voted.
I've heard phrases where I used to live in the suburbs.
In the suburbs?
Some teacher used to call it a throw coat.
Well,
A frozen coat.
that's lame.
The cheap $3 something.
I don't call them anything. I know Sigley calls them pov cake.
Yeah, that's good. Okay.
We've picked it up.
Yeah, they're pretty good. Okay. Do we want a little bit more time on this, guys? Or are we ready to go through answers? Answers?
Okay.
I have one call for answers. I have a lot of blank faces out there.
Yeah.
Okay. So I've done A, draw the graph of the vertices representing each of those towns. Explain why the graph is semi-Eulerian, not Eulerian. So the thing to do here is always just based on vertices. Like you could try and show that the paths wouldn't work, different ways, but that's going to take you a long time. So the easiest way is just talk about the degree of each vertex. This one has degree 2, 1, 2, 3, 4. Degree 2, 1, 2, 3, degree 3, 1, 2, 3, degree 3. Okay. Explain why this graph is semi-Eulerian, not Eulerian. Well, we've got to do a sentence if it's asked us to explain. This graph is semi-Eulerian as it has two vertices with an odd degree. That's all that is why. There's nothing more to it. There's two vertices with odd degree makes it semi-Eulerian. Write down an open trail that begins at Tulangi and follows every edge only once. So, if I start at Tulangi, where do I have to end up? And why is that? Because if you have a semi-Eulerian graph and you start at the first odd vertex, you always end up at the second odd vertex. So I know that I'm going to end up at King's Lake eventually. So I don't know, I'm going to go T to H, H to YG. I might get rid of this vertex now, this edge. I'm going to go YG to T, then T to K, and then from K to SA, SA to YG, and then YG to K. Have I managed to use all the edges? Yep. And I've ended up at King's Lake. Explain how you could tell this trail would end at King's Lake. Well, in ask for another question, I have to give another sentence. This semi-Eulerian trail will always end at the other odd vertex, which is King's Lake if you start at what's called Tulangi. That's all there sort of is to that one. Are we alright with that idea, guys? We feeling alright with Eulerian, semi-Eulerian?
Yeah.
Yeah, Brody is. How about
Nah, I'm all good.
the people not saying? I know that there's a lot of language around these ones, and I don't want to go too fast if you guys are not sure. good, girls?
Okay, yeah, you got as soon as I know I'm cool.
Okay,
Yeah,
now, I believe we started on question 1, but I don't think we got through all of question 1 and 2 on Monday. So for the next, I'm going to say 10 minutes, we're going to work on question 1 and 2 in your textbook. So we did start on these the other day. Yeah, I'll put on a timer for 10 minutes. So, where'd you get up to the other day, boys?
Oh, as I started 2.
Okay, sweet.
We finished 2. No, we didn't.
Complete stop at all those solid lines.
Wait, make sure you give way.
And also, don't worry about stalling, because I stalled 3 times and I still got it. So.
Oh my god, the stand's low here.
Oh, alright.
So, what is there one road that child and you just go screw it, done.
I'm not from Charters Tower, that mine is Brisbane.
Oh, stop that. You had to wait like 3 weeks just for.
I think
And then,
I
you get a strict as teacher.
failed my first one, and I think the next available one was 2 months later.
Holy.
It's like there was 3 instructors for the entire region.
Where
But you
what?
in year 12, when you got
No, I didn't get it till after year 12. I was really slow. I wasn't. I just hated
Yes,
doing
Blake.
driving lessons with my parents.
Hey, that's me.
So I'd done most of my hours, and I was like, no, I'm not getting back in the car with you. And so I had to wait.
Fake them.
Sorry?
Fake them.
No, I ended up having to wait till I got a job so that I could pay for like proper lessons. Yeah.
You just failed them.
Well,
I
because
think I did 20 max 3 hours.
I actually like.
I did about 50.
What's that? This shows my age. I was the first group of people that had to do the 100 hours. Before that, you just like got your learners at year 10, and then you just went and did the test. But no, my dad used to be like, "Oh, I need to go down to the corner shop, drive me. We'll put it down as an hour." So like, drive 2 minutes to the corner shop, he'd grab the paper, we'd drive back, and that'd be an hour.
2 minutes. You convert K's into hours.
Okay. Sorry?
Degrees. Well, they were just signed for degrees. No,
You just say like deg bracket. Like, so you'd say like the deg of A equals 3 or so.
So we did this the other day.
Yeah, I know. That's why I said I think most people got like part way through question 1 or finished question 1, but not everyone got done with question 2. That's why we've got to listen. Guys, we're gonna finish. When that timer goes, we're moving on to the next topic, and we won't come back to this till it's time for like revision. So let's make sure we're using this time productively. Oh, goodness.
Excuse me, sorry.
That's a bit rude.
Said excuse me, sorry. Jeez. That's snap. Wait, this isn't good area.
Which one?
I think it's this one. This is
So we've got 1, 2, 3, 4.
no, I just want to bring them.
Oh, what
You
is
got
it?
it.
3, 4, 5. 1, 2, a semi.
It is it? Yeah, I thought it had to be a pair of them.
Yeah, so
I had
there's
my dumbbell.
this one has 3
Can you use that as well?
and this one has 5. So there's 2 odd ones.
Oh, I thought
They don't
had
have
to be
they don't have to be
semi.
the same, no.
Oh, okay. I thought they had to be like 3 and 3.
When we do simple graphs, like small graphs, it often ends up that way just because you can either have a degree of 2 or 3. But then when, obviously the harder ones. We've got about 4.5 minutes left on this, guys.
So there's a 2 of them just after you the same.
So in that question 2, I think it's a degree of 3 and then a degree of 5. But that's still 2 odd. So that's fine. Okay, Braden, Vincent, let's stay on task, boys.
I think you guys just said G and C. Then I can break it even up. C and C. Yeah, we go between G and C, then make that 6, then make that 4. Let me read. Name of the law.
Oilarian. Like oil.
Yeah, I don't even try to G and C. Because then I'll make it 80 number and then 70.
And then what's that? What is the name of the oil? It's a weird name.
And it's spelled like EU and then Europe.
Urolarian.
It's a Swiss last name. It was from Switzerland, Leonhard Euler.
Next one?
That's it. Done. Top of the class, boys.
Unless we got it wrong.
Did I write the textbook? No. Why is there a mistake in it? Uncle Sickly.
Oh yeah, my mom said that.
Okay, 2 minutes left, guys. Still got some people still going, some people finished.
Yeah.
Okay, we got a minute left, guys.
You do concreting at 8 o'clock in the morning
Oh, I'm listening.
for about 3 hours. If you saw I forget what's called, bunting over there, that's where we're doing it.
3 hours.
Yeah, there's 3 chairs, so one there, Oh, 2 there and then 1 there. So that's like that edge.
This is part of the time.
Constructions. Gonna be testing out the old hamstrings. Be screaming.
Daniel.
I mean, screaming's not particularly hard.
I would be amazed. Like, I don't listen back to these recordings, but I wonder how much of the recording is just you two talking about random stuff.
Oh, shit.
Of it.
I think you've been using that way.
No.
Alright, let's go on, guys. So, it was.
Oh, that's fat, sir.
Okay. It is.
Brooklyn has the best show in the world. Hands down.
Righto, guys. Eyes up here, please. So, we're going to talk about Hamilton's puzzle. So we had the Swiss Leonhard Euler for the last one. This time we have the Irish mathematician William Rowan Hamilton in 1857. The goal is to find a path through the graph that starts and ends at the same vertex and visits all vertices exactly once. So you can only visit a vertex exactly once. So in 1857, Hamilton's puzzle was commercially produced as a board game called the Icosian game. Numbered ivory plugs were put into the board to mark out the path that you'd taken. There are only 4 of those boards known to still exist. Because of this puzzle, any path through a graph that visits every vertex of the graph only once is called Hamiltonian. So if you can go through a graph and only visit each vertex once, it's Hamiltonian. If you're only visiting each vertex once, can you ever reuse an edge? Because that, by definition, would be going back to a vertex you've already been to. Okay, so a Hamiltonian graph contains a cycle called a Hamiltonian cycle that involves every vertex of the graph. It allows you to begin at any vertex, visit every vertex only once, and return to the starting vertex. A semi-Hamiltonian graph contains an open path called a Hamiltonian path that involves every vertex. So you begin at one vertex, visit every other vertex only once, but you don't return to your starting point. So this is sometimes also referred to as the traveler problem or the traveling salesman problem. So imagine you're going from town to town selling something. You don't want to have to go back to a town you've already visited. Not for nothing, but the solution to the traveling salesman problem, if you can prove it, is worth $1 million. Wow.
It's not bad.
High levels of listening there.
I was listening.
So a version of this problem, like it's obviously a little bit harder than what we're going to do, it's called the traveling salesman problem. If you can solve it, it's worth $1 million.
It's worth $1 million.
No one's ever solved it.
So it's not possible.
It's possible, it's just no one's ever
Well,
done it.
how do you know it's possible?
It's mathematically possible.
Well, theoretically it's possible, just no one's been able to prove it definitively that it's possible.
I will be the one.
Yes, please. Can I get you to get down Hamiltonian and semi-Hamiltonian?
We get $1 million if you solve it.
Not this one.
Who will I have to go for the $1 million?
Alright, so let's get those definitions down, guys. So foundation, there's like, I think it's down to like 8 problems called the Millennium problems. And if you can solve any of them, it's worth like $1 million.
That was so.
So I think like one of them's called the Riemann hypothesis, but that's like super complex. It's like you have to prove that all non-imaginary coefficients of this particular equation are equal to a half. Something super weird.
Well, the coefficient of determination.
Pretty much. Like, honestly, I studied a maths degree and I couldn't tell you what the Riemann hypothesis is actually about. I think I might have known once, but that was many years ago. go. But traveling salesman's pretty cool.
Look down the definitions, but unless
Yeah.
in your book.
Traveling, no, because it's a theoretical problem. Like it's basically like it's more practical than what we're doing. But basically, the idea of the traveling salesman is what is the best path in all cases. So like basically come up with a formula that no matter what the situation is, it'll give you the quickest path through the network. So if you can come up with like an algorithm that will always get you the right way. So yeah. Yeah, I think it actually might be more than $1 million now. It was $1 million like 10 years ago.
Interest that around the world.
Man, it might have gone down right now. There's economies and shit.
Are we trying to trade the UK now?
Let me see the video. Because I will give you biscuits with YouTube.
Oops. What it doesn't say up there, unlike an Eulerian graph, you don't need to use every edge, so you can leave edges unused. That's allowed. You just need to visit every vertex once and not repeat any vertices. I'll give you another minute or two to get those down. So just Hamiltonian, semi-Hamiltonian. So very similar to Eulerian, just with vertices instead of edges. Eulerian, that might be a way to remember it. Eulerian's about edges, E and E. Yes. Do I watch anime? Not really. I have watched a fair few Studio Ghibli movies. They're pretty good. They're a bit like, you can tell it's definitely a different culture, the stories. There's some random stuff in there. I watched that a month or two ago and I was just like, what the hell is this? Oh, I saw that one years ago.
What is it?
I don't know. I'm not usually one thing
Actually, when I was a kid, I used to watch One Piece on like morning cartoons before school.
That's old.
One Piece, and they've just put it on Netflix. So just like the other day, I was like, I'm gonna watch it, and I'm like halfway through the first season. I was like, this is terrible, but I'm gonna keep watching it.
So it's like season 10 or something. There's like 1,000 episodes.
Yeah, there's lots of yelling. It's a very yelly show.
you're the volume now.
Yeah, that might be one to turn the volume off, just subtitles. Alright, I'll give you another minute on this, and then we'll have a go at that sheet that I put in front of you. So, if you've got that done, actually, I'll just tell you now. That path, that thing there, is the same as the game that Old Mate created. So what I want you to do is use a highlighter or a pen. I want you to choose a place to start, and see if you can find a Hamiltonian path through that network. You found one already? Oh, let's check. I thought it would take you a couple of minutes, but apparently you're in big brain mode. Whatever. That's the traveling cells and problems are the more difficult version. Ooh. No, I didn't. To be honest, people that have dedicated their lives to mathematics haven't found it in 50 plus years. That's plenty of people do. Ooh. One of the other millennium problems, the Riemann hypothesis, is this really famous mathematician Riemann proved something, but he didn't write down how he did it. Which is one of the millennium problems is, can you like find the proof that this guy came up with? Like, so can you figure out how it works, and then like write out how it works so that everyone knows? Because at the moment, like, that's why it's called a hypothesis, because like it's speculated that it's true, but they can't prove it, which is kind of funny. But, so the Riemann hypothesis, that was the one I sort of mentioned before, where you've got that doesn't count, Sigley.
Yeah. Own it.
So the Riemann hypothesis, basically, it has infinite solutions. So it's this sum, like this equation, and if you solve it, there's infinite different solutions to it. But in each of those solutions, there's an imaginary component and a real component. And somehow the real component is always 1/2. And you have to prove why that is. So you could there's two ways you could get the prize money. You could either prove that that's not true, so contradict it, or you could prove mathematically that it is. So there's this whole branch of maths called pure maths, where they don't, like, you'd never touch a calculator. You don't even think about numbers. So they use only like X's and Y's and stuff, and they can prove, and so that the whole branch of pure maths is about proving things.
Right, so for Hamiltonian graph, you have to use every edge as well.
No, you just need to get to every vertex. So you manage
Yeah.
that.
You have to return to
Yeah, just return to your starting
Have you watched all two?
that like semi.
Most of the day.
So you've gone to every edge, but haven't
So
you need to buy every vertex, but to get back to your starting.
Did you not like it? No, I liked it. I loved it. It was such a good show.
You had any luck?
I haven't. I gave up after 2 tries. I missed one vertex.
Yes.
Yeah, get to watch that, and then we need to watch something that I'm going to show you that's like really fun. It's really good. Remember that first one we watched out? How'd you mention it again?
I would say you as a person as well.
Yeah.
Designed it.
It's like it was 3 parts of
You did it first go. Wow, that's pretty impressive.
Next time we go camping, get the projector.
That's one. There's a few different ways you can solve it.
I have a projector.
Yeah, there's a few different ways.
Let's get a big white down.
That might give you another 2 minutes.
Wait, we only have to hit every dot.
Yeah, every dot.
Yeah, you just got to hit every dot once.
I was thinking it.
How we going, girls? Found a solution yet?
I'm a rule breaker.
Alright, one more minute.
Put it inside first. No, you can't do it inside first because that's good.
I think I got it.
Well, you can start from anywhere, right?
Yeah. So Hamiltonian and your Eulerian, you should be able to start from anywhere and do it.
Fun way. Well, time pretty quick. 25 minutes.
Oh, I got it.
Did you actually?
Yeah. So I started here. I went dish.
Yep. Nicely done. Okay.
Well done.
I think most of the tables have got it. Let's keep moving, guys. We do only have 20-ish minutes left. 25 minutes left. Okay. Okay, we're gonna have a... Thanks, guys. We're gonna look at that same map as before, but this time we're gonna talk about whether or not it's Hamiltonian. So can I visit every vertex once and end up back where I started? And what I want you to do is write down at least one Hamiltonian path and then one Hamiltonian cycle that begins at Healesville. So you should begin and end at Healesville, visiting every vertex once. Actually, after that, what are we going to do? Ooh. Actually, no, I just want to go through this really quickly and I'll let you do independent work. Let's have a look. So this is our graph. It's the same one. Can you see? I could literally just go around the outside. I've visited every vertex once. As boring as. Write down a Hamiltonian path. SA to YG to H to T to K to SA. Write down the Hamiltonian cycle. It begins at Healesville. H, T, K, S, A, Y, G, H. I just saved us 10 minutes. Okay. So, challenge. How many different ways are there? Visiting each of these countries once and once only, beginning and ending at Australia. So if we start at Australia, how can we make a Hamiltonian path through that, essentially? How many different ways do you reckon there are?
One.
It's more than one, I think. Three, four. Let's see. Three? Who votes on there's going to be three answers to this? We got 3 people for 3? 4 people? Who reckons might be more than 3? 4 people? Anyone reckon, those people that reckon 4 or more, how many do you reckon?
36.
4 or 5? 4 or 5. Let's see. Let's start in Australia. We could go to Brazil, then to China, then Denmark, then Fiji, then Ethiopia. We could go Australia, Brazil, China. No, we couldn't. We could go Australia, Brazil, Fiji, Ethiopia, Denmark, China, Australia. That's 2. Australia, Ethiopia, Fiji, Brazil, China, Australia. That's 3. Australia, China, Denmark, Fiji. Australia, China, Brazil, Fiji. So is that 4?
Australia, China, Denmark, Erie, Fiji, Brazil.
So is that 4 that we found total? 5? Oh, because really you could go Australia to Ethiopia and then go that way or go that way, which would be 2 separate paths. Or you could go straight to Brazil, which would be 3, or straight to China, which is 4. Once you get to China, you're sort of stuck, because you have to go there and then and then and then.
Not really.
So if you went Australia, China, then more than one way you can go.
Yeah, Australia, China, Denmark, Erie,
Ethiopia.
Fiji.
Oh yeah, down. Yeah, you know, right, you are. So there's more than 4. There's 5. There's 6.
It's going to Erie. To Erie, mate.
Okay. Your other challenge is to prove if that little text message chain thing is Hamiltonian, semi-Hamiltonian, or either. But also, can you go to page 422 and do question 1, 2, and 3? And that'll be us for today.
How long do we have? So how long do we have for this? Less than
20 minutes.
Can I quickly go to the bathroom? So I go to the bathroom.
Nathan's so spiteful.
Bye bye.
it's so big spiteful.
Do it.
Being spiteful.
What's that mean?
Means you're acting with spite.
What's spite?
Yeah,
I don't know what to do things like what?
I don't think we had you to listen to you made the joke.
Dude, if Nathan's not brave enough to say it to my face, it's
No,
Yeah.
even that.
Yeah. No, that's a.
No. Even that. That's that.
No, it was. I don't think we had it.
spite is where like
Because I'm not going to kiss him in the toilet.
Yeah.
Yeah. They'll kiss him in the toilet.
No, we got pulled down to the office and they didn't tell us what for. Both me and Nathan know it.
vaguely. It wasn't in mine, me told me that.
Yeah, and then I was like, Mom, I just want to tell us and Nathan was looking at me and then I was like, we were called kissing and stuff.
Anyway,
That's what he
but
was saying.
spiteful is like if you like, if I didn't like you, so I was just like, I told
Do
you all
something
the
out of
time.
that.
So it's
So
like,
like petty.
yeah, like you're being spiteful.
If you're
So
doing
petty.
I really like calling people spiteful. It's my favorite thing.
who's spiteful?
Miss out always spiteful. Actually, don't tell us that. I call her spiteful. You won't get away with it. I get away with it.
Nathan gets away with it.
Oh yeah, I am.
Yeah, she loves me. She gives me good parts all the time.
It's quite spiteful.
You know what? If I don't teach you anything about maths, but I send a bunch of adults out into the world using the word spiteful all the time, I'll kind of feel like I did a good job.
Which makes Shelley quotes.
What are we going to do for like week 6 and 7 when we don't go to, yeah.
6 and 7.
Have a
Party.
party.
No, that's.
Just have a 3-week party.
Don't we have to do? Oh, are you talking about next, not next time, the time after?
Yeah.
Yeah, time 4. Like, graduation. You better throw us in that party, otherwise.
Yes,
Or like, completely. What's your favourite movie, sir?
My favourite movie.
Really good movie.
51st day.
Watch White Chicks.
Yeah.
White Chicks.
Wanna watch White Chicks?
No.